In our previous lessons, we have been looking at the measurements in terms of their units. We've talked about the units of measure, the SI units, derived units, and we've talked about the deriving of volume, the deriving of density. We've talked about the units of measurement. What we need to talk about is the other very important component of measurement, and that is the number associated with the measurement. Because the measurement is going to have those two things. It's going to have a number and it's going to have a unit. So let's spend some time talking about the number world today. And we're going to look at scientific notation because we have to use that a lot in chemistry. It is useful when you're dealing with really large numbers, which we use a lot in chemistry, and really tiny numbers, which we use a lot in chemistry. So we'll talk about scientific notation. We'll talk about when you make a measurement, how reliable it is. You can't look at a burette and know to 15 significant figures or 15 digits the volume of that substance. There's a limitation by your measurement. And then we're going to learn at something called a significant figure and how to count how many significant figures are in a number. Okay, so let's go through and start examining these components. Let's start with scientific notation. Okay, so when you're dealing with, for example, 12 grams of carbon, 12 grams of carbon would have, you see that number on the screen? A huge number of atoms within just 12 grams of carbon. And 12 grams of carbon you can easily hold in your hand. It's no big deal to have a little pile in your hand. So this is a very large number. And it would be very cumbersome to have to write, every time we wanted to write this number, this all the way out. So this is scientific notation right here. And in scientific notation, what do? We place a decimal point after the first non-zero digit, and then we count how many places we had to go from where it was to get over there, and there'd be 23 places to do that. Now this is not just a shorthand representation. If you take 10 times 10 times 10 times 10 23 times and multiply it by 6.02, it is the number that we see there on the screen that I've underlined. So this is a true representation of that value. Now, if it is a very small number, so if we took a single atom of carbon, it would take this many grams, okay? That's a very tiny mass. And if we wanted to represent that in a way with not having to write all of those zeros or type all of those zeros, we put the decimal point after the first non-zero digit, and we count how many places over we have to move it to get to that, and that becomes this power, okay? And it's to a negative power. What does that mean? This is equivalent as to 1 over 10 to the 23rd. Sorry, I didn't get my 10 in there. Let's get a 10 in there. This would be equivalent to this. Okay, those are the same things as we see there. So if we took and did 1 divided by 10 times 10 times 10 times 10 times 10, okay, it's a very small number, that would end up, when we multiply by 1.99, with this actual number. So this is not just a representation of this number, it really is this number, but written in a way that we can handle, and also written in a way that our calculator can handle. We could not put this number into our calculator. There's no way, but we can easily put this into our calculator. Now, so when you write it in scientific notation, the n is some number, okay, between 1 and 10, okay? It's not going to be 10, but it's some number between 1 and 10, and then you'll have times 10 to some power, and if the number is very large, it's going to be a positive integer for the very large numbers, and it will be a negative integer for the very small numbers. So that's scientific notation. Now, many of you have used scientific notation in the past, and you're familiar with it. But I want to make sure you're fully familiar with it. So let's consider that there is an appendix in the back of your book. It's Appendix 1, and at the very beginning of this appendix, it's going to be talking about scientific notation. This appendix has got all kinds of common mathematical operations that you use in chemistry, and I would recommend every one of you to do a scan through Appendix 1. But today I'm really asking you to emphasize the exponential notation or the scientific notation. So look at A1 and A2. These are the first 2 pages of that appendix, and review these pages. Some of you will review it and say, oh yeah, I remember that, I remember that. And some of you are like, oh, I don't remember seeing that before. Let me examine it real closely. So look through those 2 pages. It's just 2 pages, okay? It's important that you can work with scientific notation when you're doing calculations. You'll need to take 2 numbers and multiply them together, and they're both in scientific notation, or multiply this by and divide it by the other number in scientific notation. You need to know how to do that. Or take a number in scientific notation and square it or cube it, and you need to know how you handle those. This appendix will review those concepts for you. Things you should have learned somewhere in your past. Doesn't mean you remember it all and you're going to be using it. Okay? I want to make sure you bring a calculator that is approved for this class to class next time. There is a list of the approved ones on the computer for this class, as well as in your syllabus, so make sure you look and see. If you have any questions about that, you may ask me about that. But I want you to bring that calculator to class, because way too often I see students 2 semesters into general chemistry who are not using their calculator correctly. They are not using the buttons that are useful for scientific notation correctly. They are causing themselves a whole lot more work. So we're going to spend some time in class actually making sure we are using our calculator correctly to bring it to class. Okay, let's talk about reliability of measurements. So what I have here is probably a blow up of what we call a burette, or it might be a graduated cylinder. And we see here that the liquid is rising up to some point in this, and we want to be able to measure it. If you look really closely here, and let's just zoom in a little bit, okay? If we look really closely here, we are seeing that it dips down and rises back up, and we call that dip down a meniscus. Okay, so what we need to think about in terms of a measurement is we can only make a measurement as good as the markings on this device. We have these markings coming up here, and there's a certain number of those markings. Okay, so in a scientific measurement, you're going to report every digit that you can know certainly by looking at the scale, and then estimate one more place past that. So again, we're going to blow up into here. And I see very clearly that this is somewhere between, and I can't write when I'm blown up apparently, somewhere between this mark here and this mark here. Okay, now let's think about what those marks are. We have 4, and this is 4.1, 4.2, 4.3, 4.4, 4.5. It's between 4.5 and 4.6. So I know it's bigger than 4.5. Okay, so it's somewhere between 4.5 and 4.6. I know that with certainty. What I'm going to do is I'm going to estimate the last place. So in my mind, I take this little guy and I do 10 equal marks between here and there. So I'm visualizing 10 little marks between here and here. I'm not going to write them in. I'm just going to say, all right, if I, in my mind, divide this in 10 marks between here and here, I want to consider, where do I think this spot right here falls, okay? So we would do a little bit of an estimate for that. Now, when I look at it, I might say, okay, it looks to me like it's 4.5, it's bigger than 4.5 certainly, and it's not all the way up to 4.6. So what I see here in red is my estimation. I'm saying it's a little bit more than halfway, and I called it a 4.7. But you can see, if we look at that this is nothing more than an estimate, me doing the best guess. You might look at that and call it 4.78 or 4.58 or 4.56. You're not going to necessarily pick 7, so that last digit has a little bit of uncertainty. Okay? Down here we see a thermometer being read, and in this thermometer we can know with certainty the 103 part. So let's kind of zoom in on it and let's see that. So here's the 100. 101, 102, 103. I know that part with certainty because my scale is telling me that much. But then I have to estimate, where does that last digit fall, okay? So I made an estimate that is falling a little less than halfway there, so I call it 103.4. Now, what you need to do is get comfortable with the fact that I can only know the measurement to that many places. And if I threw that number into a calculation, my calculation is going to be limited by how well I know this measurement. I can't multiply by 5 and divide by 9 and come up with something on a calculator that gives me lots of digits and say, oh, all of those make sense. You can only know your calculation based upon how well you know your measurement. So a lot of people want to keep all of these digits in a calculation and write them all down and say, if I were to let go of any of them, I'm being less accurate. Well, you're not. You're being less accurate when you keep them all because you can only know the measurement as well as you know the measurement of the devices you're using to make that measurement. So when you put them in a calculation, you've got to be able to count and keep track of those digits, okay? So let's, like I said, what I've estimated is there in red. Let us talk about, okay, a measurement's already been made and we're being given these values. How do we count how many significant figures it actually has? Okay, so we're going to go through this process. These are steps that we have to keep in mind. The first one is easy. If it's not a 0, it's easy to know that it is significant. If we look at this measurement, it has 4 significant figures because none of them are zeros. Now, if there is a 0, but that 0 is in between non-zeros, that's what we're seeing here. I have a 0, it is in between non-zeros, that will definitely be a significant figure. So when I look at this number, 606 meters, it has 3 significant figures. The rest of them deal with the 0 because the 0 is our iffy thing. Is it significant or is it not? This 0 certainly is. The next one, it's zeros that are not significant, okay? So we're emphasizing the word not. If they are to the left of the first non-zero digit, then they are not significant. So I'm looking at this number, looking at it from left to right. Here's my first non-zero. Any 0 to the left is not significant, and this has only 1 significant figure. And this is so hard for students to remember. When they see a number like 0.012, they want to call that 3 significant figures. They know not to count this one for some reason, but they want to count all of those. And that is not correct. This one would only have 2 significant digits. Okay? Now, trailing zeros. If there is a decimal, and this is important, okay? If there's a decimal point in that number, trailing zeros are significant. Okay, so I have a decimal point right here. These are trailing zeros, meaning zeros after the last non-zero digit. So those 2 are significant. And it doesn't matter whether that 0 comes before the decimal point or after the decimal point. As long as there's a decimal point in there, those are significant. So 240.0 has 4 significant figures because trailing zeros are significant if there is a decimal point in there. If there is not a decimal point in there, you cannot say with certainty how many significant figures this thing has. We know with certainty it has 2. No problem, this has 2 significant figures, and that's all I know with certainty. But if the person wasn't careful, and maybe there were more significant figures, if the person wasn't careful, we wouldn't know how many beyond the 2 it would have. Okay, so we know this one has 2. Now, how could I write this so that I wanted to say all of them were significant? All I would have to do is put a decimal point right there. Now it meets the criteria up here. There's a decimal point, and all trailing zeros are significant if there's a decimal point. So as soon as I put that little dot right there, we suddenly know that this number is going to have 6 significant figures. Well, what if I wanted it to have 3 significant figures? How would I designate that? Well, if you've got something like this and you want to represent it with 3 significant figures, you have to convert it to scientific notation. Because as soon as you start convert it to scientific notation, we're going to move it over 1, 2, 3, 4, 5 places. Okay? This number now can have 3 significant figures. It has a decimal point, it's a trailing 0, and now I know that one of those zeros was supposed to be significant. So converting over to scientific notation is the best way to take a number where it's ambiguous and correct for that. Now, if you're looking at the number that you see right here as it's written, you can't doctor it up and say, I want this number to have 5 significant figures. You don't know. All you know is it has 2. So if you're making the measurement and you're reporting the data out, or you've done a calculation and your answer on your calculator ends up being this, but you know your answer should have 3 significant figures, it's going to be important that you convert it on over to scientific notation so that the person knows it has that number of significant figures. How many significant figures are each of the following measurements? All right, so a person is making a measurement. I'll see if I can, oh, there they are. Okay, here we go. 6.4 times 10 to the 4th. Think about it. What do you say? Did you say 2 significant figures? You'd be correct. A thing to point out. This part tells me nothing about significance, nothing at all. All it's telling me is where that decimal point lives. That's its job. So this is equivalent to 64000. That is the number, but it has 2 significant figures. The 10 to the 4th is not telling me significance, okay? Here is 560 kilograms. How many significant figures does that have? Well, if you are looking at that as it is, we can only know it has 2. It's too iffy about that third one. But if you wanted to show that number right there having 3 significant figures, and you might have been looking down here at this going, oh, I know the answer. But if you wanted to show this as 3 significant figures, you would either put a decimal point at the end, or you would convert it to scientific notation. Now, this is a case in which scientific notation ends up being a bigger thing than writing it out this way, but at least it tells us about significant figures in that number, in that measurement. Here's another one for you to pause and ponder. Look at this and decide which one of those is the correct answer for how many significant figures are in each of these 3 numbers. After you've figured it out, resume your video. Okay, did you come up with the answer number 3? Then you'd be correct. This one has 2, the second one has 4, because the zeros are in the middle. This last one only has 3, and if you were going to miss one, I would guess that'd be the one you'd miss, thinking that that one might have 4, but it only has 3. And before we finish our discussion on significant figures, the last thing we need to discuss are exact numbers. In exact numbers is a counting number, okay? These numbers are defined straight up that way, or you've counted objects, okay? When you have something in that situation, they have an exact number of, an infinite number of significant figures, so we'll say it that way. You could say how many eggs are in a dozen, and you would know it's 12. That is by definition. Is that kind of 12? Is that somewhere between 11.5 and 12.4? No, it's exactly 12. So we wouldn't say that just has 2 sig figs. We would say it has an infinite number of significant figures if we needed to use that in a calculation, because it's exactly 12. Some other examples, okay? We could maybe in a calculation have to calculate an average. Now we know that when we do an average, we add up our values and divide by how many objects we have. We haven't got into all the rules for significant figures in a calculation, so I'm going to have to kind of briefly mention one of them. If we were to add these 3 digits together, okay, our rule for division is that you go by the least number of significant figures. And so some people, after they've learned that rule, might look at this and say, let's consider this as being the answer of 7. It wouldn't be, because there are 3 measurements. That's an exact number. So we could write this as 3, as many zeros as we wanted to forever and ever, and that would be just as accurate. And so we don't want to tag in on that 3 when we're doing calculations with exact numbers. So if you're given a number that is based upon a definition, there's 12 eggs in a dozen, or it's a counting number, like I want to count how many eyes you have 2, that's exact, then those exact numbers have an infinite number of significant figures. So measurements have units, we've talked about. Measurements have numbers. We've learned how to report those numbers with scientific notation, and when they have been a measurement based upon integrations on a scale, we know that we have numbers that come off of that scale plus one additional uncertainty one where we do an estimate. All of those are significant. They tell us something about that measurement, and so we know how to count those significant figures once we've seen it written down on paper.